So now that we have a little bit of understanding of what a differential equation is, let's talk about how we can actually model some situations. And so we're going to use differential equations to model them. These are called mathematical models, and this is where we're going to describe a system or phenomenon in a mathematical terms. Now, when we say system, it doesn't mean we're getting a system of differential equations. It means like that situation you're doing, like I'm dropping this pen. That would be your system. It can result in multiple different equations in a system of different equations, or it can result in one different equation. And what we need to do is we need to read each situation and see what it is. There's no, this is how you do every single problem. It's more of reading the problem and trying to come up with some ideas. So let's take an example. At a certain time, a technological innovation is introduced into a community that has a fixed population of people. We want to determine a differential equation for the number of people who have adopted the innovation at some time if it is assumed that the rate at which the innovation spreads through the community is jointly proportional to the number of people who have adopted it and the number of people who have not adopted it. So what we have to do first, we have to figure out what are our unknowns, what things we're dealing with here. So we're dealing with the number of people in the community. So let's start off with that. Let's give it a name. Let's first write down, we're dealing with the number of people. And I'm going to call it n for number. And actually, I'm going to go a little bit more than this. I'm going to actually call this n of t because it's the number of people at time t. So I used n for number. You can use any letter you want in the world. It really doesn't matter. I like n. I like letters that mean something that goes with what I'm dealing with. So I don't usually letter x's very often. I use t for time, just because t and time makes sense. Then we also have an idea of that we have the total population. We have a fixed population. So let's give that a name. Because I like population, let's use P for population. So P is the size of the population, size of the community, let's call it. And then we're looking at a rate. So every time I see that word rate, that rate means a derivative. So we're taking the rate at which it moves to the community is the derivative of the number of people who have it over time. That's that rate we're looking for. So dn dt is your rate at which the innovation spreads to the community. We're told it's jointly proportional. So proportional means we're going to have some constant here. Give that constant some name. I'll call it k. I don't care what you call yours, as long as it gives some name. And it's going to be jointly proportional to the number of people who have adopted it and the number of people who have not adopted it. So we know what the number of people who have adopted it is. We call that n of t. Jointly proportional just means we're multiplying these together. That's what jointly proportional means, or directly proportional, just multiplying these two things together. So we need something else here. We need to look at, we're jointly proportional to the number of people who have adopted it. That's what n of t is. And I should have said who adopted. Adopted. Can't spell adopted. Okay. And we're looking at the number of people who have not. Well, if we have P people in the community and n of t have adopted it, then the number of people who have not is P minus n of t. So if n of t is how many have adopted it, P minus that is how many people have not. And so there's your differential equation. Now we are going to make one little assumption here. The assumption we're going to make here is that at time 0, there were 0 people who had adopted it. That's probably not the safest assumption, but that would give me my initial value. All right, let's try another problem. Suppose that a large mixing tank initially holds 300 gallons of water in which 50 pounds of salt have been dissolved. Another brine solution is pumped into the tank at a rate of 3 gallons per minute. And when the solution is well stirred, it is then pumped out at a slower rate of 2 gallons per minute. If the concentration of the solution entering is 2 pounds per gallon, determine a differential equation for the amount of salt in the tank. Also state the amount of salt at the start. So we want to know the amount of salt. So that's what we're going to deal with. Let's call that A of T. That's the amount of salt at time T. And that's changing because we are pumping things in and out. So that's why I know that this is at time T, because it is changing over time. All right, and so that's what we have. We want to look at, it obviously is changing. The amount of salt that's in the tank is changing over time because we've got things going in, we got things coming out. It's changing over time. So therefore, because it's changing over time, that means there's a rate of change. So the derivative of A with respect to T being my independent variable, is what we have. And now what we want to look at is how is that changing? Well, we have stuff coming in and we have stuff going out. So the rate of change is based on how much is coming in and how much is going out. So it's going to be your rate in minus your rate out. And the reason I can say this is positive and this is negative is because in are things that is accumulating, it's going in, it's adding to it. Out means it's being subtracted away. So that's why it's minus. So we have this rate in and minus the rate out. So if we can figure out what those rates are, we're in good shape. So let's look first at the rate in. All right, so let's go back up here and see if we can figure out how much is coming in. Well, we know it's coming in at a rate of 3 gallons per minute. Well, that's cool. So we already know the rate in. It's 3 gallons per minute. Well, here's a slight problem. And my slight problem is I know I have 50 pounds at the start. So the amount of salt in the water is 50 pounds. And I now have a rate in as gallons per minute. Well, if A is the amount of salt and that's in pounds, then this dA dt is pounds per minute. But I have gallons per minute. So I actually use my units to help me figure out how to get these together. I want pounds per minute. I have gallons per minute. So let's see if we can figure out how we can change that in from pounds per minute, from gallons per minute to pounds per minute. And so one thing I notice is I've got the concentration of the solution that's entering is 2 pounds per gallon. So I know I have 3 gallons per minute coming in times 2 pounds per gallon. And what I see here is that my gallons cancel and I'll be left with pounds per minute. In fact, I'm left with 6 pounds per minute. And so what I notice is, again, dA dt will be in pounds per minute because amount's in pounds. If you want to, you can actually write that your amount's in pounds to help you. And T is in minutes. And so you now know I need pounds per minute, and I now have a pounds per minute for my rate in. Let's do the exact same thing for our rate out. Figure out what our rate out is. The rate out is a little bit more work though, because one of the things we got to think about is we're putting this concentration of 2 pounds per gallon into the tank, but that's not how fast it's coming out, because it's going to mix with whatever was in the tank already. There was already water and salt in the tank, and we're going to put this 2 gallons in, and it's going to mix with it because it's well stirred. So it's going to be mixed with that before it comes out. So it's not coming out at the same concentration it went in. It's not coming in with that information. So we have to figure out what it is. How fast is it coming out? So one of the things we can look at here is it's going to be coming out at the amount of salt that's in there at that certain time, which we know is A of T. So that's the amount of salt at a certain time. And we do know that it's 300 gallon tank. So we have 300 gallons and it's coming in and out. So we know the amount of salt that's in there at a certain time is A of T divided by 300. All right, so we have that information. And this is pounds per gallon is what we have. But again, I need to do a little bit more work here to figure out what this is. And this is pounds per gallon, but I need to end up with pounds per minute. So I got to figure out how many gallons are going out per minute. So that's the next question is, how many gallons are coming out per minute? So one thing I notice is it's going in at 3 gallons per minute. It's coming out at 2 gallons per minute. So the net change is 1 gallon per minute. But again, that's not exactly how much is in there. That's not exactly how much is changing. So we have to look at, we started with 300. We're putting in 3 gallons per minute, and we're taking out 2. Right? So we came in, 3 pounds, with going in at 3 gallons per minute, and we're coming out at 2 gallons per minute. So we're actually adding 1 gallon per minute. So we started with 300 gallons, but we're going to add 1 gallon for every minute, so 1 T. So that would be the rate of the gallons over time. So we happen to have my gallons are changing by, so it's not 300 here because it actually is changing by this plus 1 T. So A of T is my gallons per minute, my pounds per gallon. And then we are actually taking it out at 2 gallons per minute. So we don't just have A of T because we are adding to the gallon. So it's not just A of T over 300, it's A of T over 300 plus that T times that 2 gallons per minute. And now we see we have pounds per gallon again. So we're going to end up with 2 A of T over 300 plus T pounds per minute because the gallons cancel. So now we can get our differential equation because our differential equation, dA dt, is the rate in, which we found out was 2 pounds per minute, minus how much is going out. And the rate out is 2 times A of T over 300 plus T. And there's my differential equation. If I want an initial value, how much was in there at the start? So at the start, A of 0, well, at the start, we had 50 pounds. So at the start, we had 50 pounds. So A of 0 equals 50. There's my initial conditions. So there's my differential equation. Again, every single problem is a little different, and you have to go through how to go find those and see what those are. And you can see how it all kind of fits together. And each one, hopefully this gives you some idea of how to come up with some of these.